To the Types 1 session. I think this is the first paper session. We're going to kick things off with a lovely talk by Justin Frank on generating well-typed terms that are not useless. 15 minutes. I'll give you hand gestures for 5 and 2.
All right. Hello, everyone. I am Justin, and I will tell you about how to generate well-typed terms that are not useless. But before I get to that, I want to take a bit to explain why generating well-typed terms is a useful thing to do. And that is for something called differential testing of compilers. So this is a method of testing compilers where you generate a whole bunch of random programs and feed them through 2 different compilers, and then run the resulting executables and ask, are the outputs that they give us the same? And if they are not the same, that indicates that there is indicates that there is a bug in one of the 2 implementations, assuming, of course, that our programs are deterministic. And while having 2 different implementations for the 2 different compilers for the same language might seem like a big ask, fortunately, we can just run the same compiler with 2 different optimization levels. And now we are only testing the optimizer of the compiler, but optimization passes are a large source of miscompilation bugs. So that brings us to how do we actually generate these random programs to feed to this process in the first place? Well, we built off of a technique developed by Michal Polka to find bugs in an older version of GHC. So this technique is based off of looking at the typing rules for the language and viewing them as generation rules. And so let's see how to do that by looking at the typing rule for lambdas here. So this rule says if we are generating an expression of a function type, we can create an abstraction where the body of the function is given by a recursive generation problem that we need to solve. And so one way of implementing this algorithm is by expanding typed holes in an expression in small steps. So for an example, we might start with a hole of type integer, and then we can expand that into an application where we are applying a function from integers to integers to an argument of type int. And then from here, the generator might decide to look at the function position and then expand that into a lambda with now a typed hole for the body. And then finally from here, the generator might look at the body hole in there and see that, hey, I can fill that in with a variable reference. And then from here, the generator would go and expand the argument until it has created a complete term. But let us actually rewind the process here, because this process is stochastic. And go back to the application that we first created. So when it chose to create an application, while it is constrained in the return type of the function, the argument type can be whatever the generator wants. And so the generator, in the previous example, it chose an integer, but it might have randomly chosen to ask for a function from booleans to integers. And then repeating the generation process, it could have still expanded the function to a lambda, but now it no longer has the option to fill in the body with a variable reference because x is of the wrong type. So instead, the generator might say, oh, I'm just filling it in with a random integer. And this choice leaves this argument in an interesting position in that no matter what we fill in there, the result from that expression will not be observed in the test. So the generator might fill that in with some behavior that does actually exhibit a bug in the compiler, but, well, the fact that it did that is useless for testing. And this is a real problem that we encountered when trying to implement this type of testing for a student compilers course at UMD. And we found that a lot of the test cases would fail to find even really catastrophic bugs, like failing to correctly set up the arguments in tail calls. Because in the test cases, it wasn't generating enough functions that were actually observing what was given to them. And the problem here really is that the generator needs to decide way ahead of time what arguments it's given to a function, and then only later, when it's actually filling in the body for the function, does it needs to just randomly find variables in its context that it can use. And so we want to delay the choice of what types of and how many arguments are given to the function until we are actually generating the function. So how might we do this? Well, I will walk through an example of the operation that we want. So consider this generation fragment where the generator has created a function that is taking an integer and then it is adding to it the length of some list. So what we want to do is summon a new variable y and then simultaneously replace the whole with the reference to that variable and add a binding to that variable to the function that we are generating in. And already we can see that this generation step is different from the ones before that were purely locally expanding a whole to a larger expression. And whereas this one is non-locally modifying the context that it is in. And another weird thing about this step is that we have actually changed the type of the term from the one above to the one below. And this is a problem if the function that we just changed is ever being called. Because now, in this slightly larger example, well, our call to f is now ill-typed and needs to have another argument added to it. But unfortunately, it is not as simple as just adding a new argument to all the places that this function is called, because if we consider a larger example again, here we are now, instead of directly calling f, we are conditionally choosing to call f or some other function g. And now because we have updated f, this function g here is now receiving an extra argument that it doesn't want. And so in order to complete this operation, we need to also add a new argument to g as well. And so while with examples like this, it's easy enough to hand step through them and find all the locations that need to be changed. But in order to actually implement this as something that a generator can do, we need a way of easily identifying all of these locations where the changes need to occur. And so to do that, we introduced a notion that we call extension variables. And so just as you can see, these extension variables exactly identify all the locations in this generation example that needed to be changed. But how do these work? Well, these exist as modifications to the lambda and the application rule. So let's look at the extensible lambdas first. So for this rule, here we have an extensible lambda, and this captures a notion of a lambda that during generation can have arguments added to it. And it is indexed by the triangle alpha, which is an arguments hole, which has an extension variable alpha. And then this extensible lambda has a, well, extensible function type, where the extensible function type has the same arguments hole as the lambda is annotated with. And just something to note here is that unlike the regular lambda rule, we are not updating the typing context because this lambda isn't actually binding anything. It is simply marking for the generation where arguments can be added. And because of that, these extension variables are globally scoped. And so now let's turn to the application rule. So we can see that we have replaced the argument to the application with one of these arguments holes. And the key thing to note here about the extensible application is that it requires its function expression to have an extensible function type with the same extension variable that it is annotated with. So this means that if we have an extensible lambda, it needs to be at some point called by an extensible application with the same lambda, with the same extension variable, which is what ensures that simultaneously updating all occurrences of a particular extension variable in a program will give us a well-typed program. So now let's revisit the original generation example and see how things change with these extension variables. So like before, we start with a hole of type int, and then this time we instead expand it to an extensible application. And now the generator only has one, and you can see that the generator is now no longer having to choose a type for the argument here. In fact, it is not even necessarily choosing to have an argument there. And so then when the generator expands the function type, it now expands it to an extensible lambda. And then finally, from inside here, it can choose to perform this extension operation to add the argument to the function as well as an argument hole. Okay. So to quickly summarize what we have done, the problem that we encountered was that we were generating too many functions that did not use their arguments, which made the terms that are being generated less efficient and effective for testing compilers. And the root cause of this is that the prior art had a limitation where it is choosing the types for the functions too early, before it knew what was actually going to be useful inside the body of the functions. And our solution was to use extension variables to allow us to define an extension operation where we delay choosing the arguments until we are actually generating the bodies of the functions. And so also in the paper, you can find a full formalization of the extension operation, as well as the full definition of our type system and proofs that this extension operation results in a well-typed program. And finally, our discussion of our implementation and how this complex process can be implemented efficiently, as well as an evaluation where we replicated the bug finding of the original Polka work. Oh, thank you.
Thanks, Justin, for kicking off POPL with an excellent first talk. We have a huge room, so hopefully we have plenty of questions. We've got about 4 minutes for questions. Anyone wants to start us off? We've got one from Benjamin Pierce.
What did your evaluation show?
Yes, our evaluation showed that we were able to find bugs in less time, and less tests, replicating finding the same bugs in the old version of GHC. And unfortunately, that is the only kind of existing test that we can find to replicate bugs in this domain. It is definitely a problem with this research in terms of not having necessarily the best ways to evaluate what is effective.
Is this on? Okay. Do your test cases ever generate repeated uses of the same variable, right? Because you talked about adding new variables, but sometimes you might want to see, x plus x.
We don't generate, or yes, that does happen in the generation. I don't know exactly how often it uses variables more than once. Indeed, that is one of the problems with this. We've addressed the problem of variables not getting used at all, but because we are only, because this method is adding variables with a single use, it does also have a problem of sometimes generating a lot of functions where variables are only used once.
So we have a question from Discord. How do you measure whether your results are better than those of a naive generator? And better meaning here generate fewer unused arguments?
Well, we did measure that directly. So we measured how often function parameters were used in the code that Polka used to test GHC, and found that about 70% of function parameters are unused in their bodies. And for our evaluation work, we found that about 55% of function parameters are used in their bodies. And the reason why that number isn't higher is because the exact context, the subset of Haskell that it is generating has a lot of higher order functions given from the standard library, which have types that we're not able to perform this extension operation to.
We do have a little more time, but would you mind yielding the podium so we can set up while you ask questions?
Yes.
Thank you.
Okay, nice talk. Having said a little bit more about the evaluation, I was wondering whether you could also say a little bit about the implementation. Is it connected to QuickTick, or is it a completely standalone implementation?
No, it is a standalone implementation in OCaml. Just give a brief taste of how this is implemented. It is a bit nasty where the extension variables are pointers into the expression tree, and then we just have its mutable state where we update those locations directly.
One last question.
I wonder if you've considered testing type checkers. Maybe you need to generate nearly well-typed terms in that case.
That is not something that that is not something that we have explored, but that is definitely an interesting avenue with this type of research.
All right, I think that's all the time we have for questions. Let's thank Justin's again.
We need to switch to the other place, typically on the right. Okay.
Well, we're actually still miking Adam, so I think we might have time for one last very quick question.
Do you generate higher order functions, or do you only generate first order functions, or do you only use higher order functions from the standard library?
We generate higher order functions, and this method is actually great at generating higher order functions because it is. Well, okay, maybe you should come talk to me about that later. That might be a bit too in the weeds for to get into.
Thanks again, Justin. All right, next we have, oh, you can clap, applause, deserved.